Good afternoon. Good afternoon, everyone. Welcome to our today's virtual talk. My name is Richard Neno, working here at Nature Kenya as Birding and Membership Officer. And it's a great pleasure having you today on board as Dr. Cyrus Kavwele take us through this session. Our today's virtual talk is entitled Use of Technology and AI to Monitor the Movement and Behavior of Wild Beasts. It will be a very informative and interactive presentation. And as usual, I would like to let you know that this presentation is recorded and we will upload in our YouTube channel so that later on you may revisit if you want to. And also, I will request our participants to remain muted all through the session so that we give our speaker ample time to exhaust this presentation. And also, should you have any question, any concern, any comment, we encourage that you raise them through the chat box and we will strive our level best together with the speaker for today to go through all of them. And ladies and gentlemen, allow me to let you know whom our speaker today is. Dr. Cyrus Kavwele is a tutorial fellow in the Department of Natural Resources at the School of, uh, pardon? Uh, he is a tutorial fellow in the Department of Natural Resources at the School of Natural Resources and Environmental Studies at Karatina University, a position he has held since the year 2018. Prior to this role, Cyrus served as a graduate assistant in the same department from the year 2015 to 2018. Dr. Cyrus completed his PhD at the University of Glasgow in United Kingdom, and he also holds a Master of Science in Wildlife Management and PSc in Natural Resources Management, Wildlife Management option, both awarded at Karatina University here in Kenya. Cyrus is a wildlife ecologist with broad interest in spatial ecology, movement ecology, collective behavior, and the application of machine learning and artificial intelligence in conservation of biodiversity. He enjoys linking theories with fine-scale big data to understand animal responses to human-induced perturbations. He has also published in peer-reviewed journals and presented research findings in both local and international conferences. And that's a short bio of our today's speaker. And ladies and gentlemen, it's a great pleasure for me to welcome on stage our today's speaker. Welcome, Dr. Cyrus.
Yeah, yeah. Thank you again, Richard, for organizing the thing. And thank you, Nature Kenya, and everyone who is joining this talk today. That was really a great introduction. So I'll talk about the title that Richard has mentioned, and if you allow me, I'll start by sharing my screen. Okay, right there we are. So yeah, so today I want to talk to you about developing tools to track animal movement and behavior using technology and machine learning. So one of the significant challenges that we face today as ecologists is understanding how different environmental stresses are affecting animal movement and behavior. I don't know why it's not going to the next slide.
Okay, you can try sharing your screen again. Dr. Cyrus, if you can try to share your screen again. And kindly unmute yourself.
Yeah, I think there was an issue with the internet. Sorry about that. And,
Okay.
yeah.
You can...
Yeah, let's try and give it another. Okay. I want to make sure it's going to the next slide. I don't know why. try this again.
Let's try.
Okay, let's see this. Oh, this is working.
Yeah.
Tell me whether you can see my next slide.
Yeah, it's still in the first slide. Try to move to the next. Okay, it's not yet moving.
Yeah,
Yeah,
I think
exactly. Yeah, that's okay.
yeah, it's a bit, there's a lag effect. I don't know what's really going on. Okay, yeah, sorry about that. Some issues with technology. That's why I wanted to give it in person, but here, this is what we have. So, sorry about that. So, today I want to talk to you about tools and developing tools to track animal movement and behavior using technology and machine learning. And so, one of the greatest challenges that we have currently is understanding how human activities are affecting or transforming landscapes and consequently affecting biodiversity in various parts of the world. Now it has just stopped. Not quite sure. Okay.
Yep.
Yes, you can see my second
Yeah,
slide.
yeah, we can see the Anthropocene. Yeah.
Okay, yeah, it's not responding. So most of these human activities have had a significant effect on many ecosystems or biomes, leading to loss of large mammals. For instance, in continental Europe, what we see here in this figure A, it's red color, which indicates a big proportion of large mammals that have gone extinct. And when you also look at it, cumulatively, it shows those areas that are quite developed or the developed one, they have lost quite a number of those large mammals. But when you look at, the less developed countries like in Africa, where most of these large animals still persist, there has been many that have been lost, but now they are facing a lot of pressure because of increased human activities. So at the same time, we've also, witnessed increase in temperature. So global warming also coming into play. And all this, the synergistic effect of this is that wildlife and ecosystems are being lost at an alarming rate. So this transformation of landscapes, what do they mean to animals that need such ecosystems? Think of a case whereby wild beasts move for about 600 kilometers searching for food and water, and every time they are losing part of their ecosystem. What this implies is that at some point, these populations are likely to collapse, and because of the pivotal role that they play in such ecosystems, will result into cascading effect and possibly a non-functional ecosystem or transformation of that ecosystem from possibly a grassland to woody vegetation or woody dominated landscapes. So a recent study that was done in 2018 by Duke and others, they actually tried to quantify or investigate how the relationship between animal movement and human footprint index. And what they found is that actually in areas that are highly, altered or dominated by human or they have been cleared of the pristine conditions, it's where animals tend to move in short distances. And this could be because these animals are trying to minimize their encounters with the human beings. And they looked at even the smallest of all, the air, and also all the way to the biggest of all, like the Mongolian gazelles. And the pattern was all like the same, increase in distance where there's less human footprint. So scientists have really tried to understand animal movement and just now interested in understanding where an animal moves to, from where, and at what point in time. So the tracking technology has come from a long way, dating back to the 1960s when we first had the very high frequency radio tags. Then that one was followed by the automated radio telemetry. Then came in around 1980s, the Argo system, and now the current GPS technology, which has been undergoing various developments. But all these developments have been able to, help us understand how animals move and where they move. But then the question is, then how can we track animals at a level that is commensurate with environmental changes? Because now these changes are taking place quite rapidly because of the human influence in many ecosystems. However, the current tracking tools, they have been very instrumental, and they have helped us understand, several topics on animal movement, such as the movement ecology itself, testing functional connectivity, leadership in pigeons, corridor, and connectivity mapping. Going forward, we also realize that now we have other upcoming technologies that we've been using to also understand or rather understand animal movement from a different perspective. One of these current technologies is high-resolution satellite images, which is sort of, people, scientists are now beginning to sort of try to use it as a tool to collect data about animals. This is a study done by Zhang, which was published last year. They also used high-resolution image to track wild beasts in Serengeti, or potentially to count those wild beasts in Serengeti. Camera traps, they have been here for some time. They have been very essential when it comes to ecological surveys. And now recently, we also have these unmanned aerial vehicles that have really become very critical when it comes to animal observation and tracking. But one thing about these current tools is that they collect data in so many formats and so many for instance, you can get it as in form of an audio. It could be an imagery, it could be a video, it could be acoustic data. But one thing about them is that they also present a set of challenges. And one thing is about the voluminous data that they do collect. For instance, the camera traps, you set them, and depending on the fixed rate, within a very short period of time, you collect millions and billions of images. Some of the UAVs that we have in the market, they use high-resolution cameras, which means that a very short video will be very, very, very big in terms of the gigabytes, and therefore you need a good storage for that. Similarly, when it comes also to remote sensing, especially the high resolution, you also need to think about the transmission and also the processing. Sorry, I don't know why it's not going to the next slide. It just frozen. Okay, there you go. So these technologies, they also have aspects of the cost, whereby getting a piece will also mean that you have to spend a lot of money, and possibly for the small projects that is not attainable. And therefore, you might also think of in terms of, if you want to collect the data that suits a particular ecological questions, you also might need to think of flexibility or being able to change or tweak around that tool and collect that specific data you want. But mostly the offshore devices, they don't come with that. Actually, it's very limited, and potentially it comes at an additional cost. For instance, a case of Serengeti Wild Beast project, this one unit from Colors will cost about 2,000, and that's just getting it from the seller to your house. Apart from that, you also need to think about downlink, or how you're going to get your data from the cloud. And that one, they're going to charge you about 30 euros for that. The cost itself is 2,000 euros. And therefore, if you want to get more frequencies per day, then that comes at a cost, because if you get more than 100 fixes in a month, it means they're going to charge you, which ideally translates to less than 4 fixes in a day. And 4 fixes, that is quite important. Of course, it's dirty to tell you something, but it's, given the question that you want to answer, it's quite important. Perhaps you might need to look for other alternatives. So again, all this data that is collected by these current animal tracking tools has some sort of inherent nonlinear relationship. What this means is that you can't really use the classical statistical methods that you use to analyze the data. You need to think of something else that is able to extract these embedded patterns within those variables and make sense out of it. So looking at all those challenges and figuring out, then how can we use the current tools to understand or provide some ecological insight? I thought to answer, or rather I asked myself this or rather we had this one, the first question which we asked ourselves. Then how can we convert different types of data stream to provide ecological insight? And this one, I picked a particular case whereby I focused on non-local effects of human activity on the spatial distribution of migratory wildlife in Serengeti National Park. And what I want to show here is just how we can get data from different tools and work on that data in a very smart way and extract all the ecological insights that we want. Two, we added the question of how can we integrate the different data streams to enhance our understanding of animal ecology. And this one I'll be talking about automated and repeated area observation of GPS collared animals using UAVs and open source electronics. And then on third question, we asked ourselves then, building on the second objective, then how can we use high resolution data to provide fine scale behavioral insights? And here I'm interested in understanding or rather developing a tool that will give me a near real-time classification of Serengeti wild-beast behavior using edge machine learning and long-range Internet of Things network. So first of all, I'm interested in what beast and what beast they are in Serengeti and Masai Mara, others in South Africa. But this is where we are, and I'm interested in this ecosystem because first, it's rich in biodiversity and it's ecologically important for both Kenya and Tanzania, and economically, it's also very, very important because of the revenues. However, this ecosystem is facing threat because of the human activities of encroachment into the park. As you see here, in the recent past, what we have been able to move from down Ngorongoro Conservation Area in Tanzania, actually, which is a very important area because this is where carving takes place. And they transition all the way to the Western Corridor at some point in time, and they continue, their migration up north, and at some point they cross into Masai Mara. And then from Masai Mara, they use this route all the way to the Loiter Plains. And then there's a back route whereby they move from Loiter the way to Masai Mara Reserve, Masai Mara Conservation Area Reserve, and back to Serengeti. And then it becomes a cycle depending on whether it's dry season or wet season. So each point here or each ecosystem here
Dr. Cyrus, we can't hear you. Dr. Cyrus, can you hear me? Yes, a problem with the network. Apologies, I think yeah, his connection is quite slow. Let's just try to get him back. Dr. Cyrus, can you hear me? Just a moment. Apologies for the technical hitch. Is coming back on air in a short while. I think his internet is not stable. Just a moment as the speaker comes back on board. Okay, Dr. Cyrus, can
Sorry
you
guys
hear
for
us?
that. I lost power and lost my line.
No problem. Just a moment.
Yeah.
Okay, can try sharing your screen again.
Okay.
Okay, good. I can.
I'm back now.
Yep.
Okay. Sorry about that. Before I lost power, I was talking about the Serengeti Mara ecosystems. I was talking about in the region past what we have had with movement from Serengeti Serengeti. Okay. So, but now currently, this is not possible. For instance, in part of Kenyan side, because now wildebeest cannot go back from Masai Mara to Loita Hills. This place has been lost because of intensive agriculture that has been going on. And therefore, that movement is no longer taking place. So that migratory route is no longer available for wildebeest. So also looking at other aspects or other developments that have been happening around Masai Mara, Masai Mara National Wildlife Conservancy is development of fences around different lands whereby people they want to keep their grass to feed their cattle during dry season. And in 2011, it was about 444 kilometers, and which means these roads were available for the wildebeest to transition from Masai Mara all the way towards Loiter. But then looking at it recently in 2020, this is not the case, and that migratory route has been lost because these fences have been expanded and they are moving towards the Masai Mara National Reserve. On the other side, we have the tourism pressure, especially in Serengeti, where you see these white blocks, the bright ones indicates high tourism pressure. What we see is that inside the park, we have so many transit facilities that have been set up. And they have been set up in a way that you maximize the distance to the wildebeest because you want your clients, when they come in, to be able to get that or experience route tourism session. Therefore, from a business point of view, if you set your camp away from hotspots of wildebeest, you're likely to get tourists when everyone else has the hotels booked to capacity. But that one is from the economic point of view. When you look at it ecologically, this is has an effect on the ecology of this wildebeest. So that's just from within the parks. What about at the edges? What is happening at the edges? You realize you also have these areas, like in this case, you have communities that reside outside these protected areas. For instance, here we have the Maasai community, and here we have other communities that keep livestock and also do agriculture. But there's lots of livestock incursion, especially during the dry season. And what happens is that these ecosystems don't get a chance, uh, uh, to grow back with a normal condition, or the resilience is affected because of these roots that these animals use. So even if it rains, the grass is not able to grow back, and therefore the resilience of the ecosystem it's affected by these activities. Um, I'm trying to move to the next slide. So this one leads me now to the first question, where we were interested in looking at ways we can use different data streams to provide ecological insights. And this one, I focused on understanding the human effects or non-local effects and how they influence spatial distribution of migratory species. So in this setup here, we have this one, I'll be calling this Balageti, and this one will be Tabora, and this will be Buka. And they have said based on the human activities outside the protected areas. So what happens here is that we have a community, and you can see here they have what looks like a small shopping center, and they do a lot of agriculture and also small livestock, keeping small livestock. And the same case here with Tabora, they have livestock. You can see even the cows here, and they also do a lot of agriculture. But contrarily, these other side, these are just people interested in just keeping livestock, and they don't do any form of farming. So these are the pastoral communities. So I'll come back to this as we progress. So I wanted to understand then what happens outside these national parks actually influence spatial distribution of migratory species. And in this case, I'm basing it on the fact that if then wild beasts, as they move in their sheer numbers, they find security in their sheer numbers, and therefore these edges should not be a threat to them. Hence, they should be used in the same proportion as those areas inside the core of the park. So we have this one transect here. So I had 3 transects, Balageti, Tabora, and Puka. They were all set radiating toward the core of the park. Each transect was 10-kilometer long at an interval of 2 kilometers, with first camera right at the border of the park and the community. So again, I said these ones to extract data, or rather take photos between 7 a.m. and 6 p.m. And in total, I had 157,000 images, all from the 16 camera traps. And therefore, at each camera site, I also extracted a change in NDVI and grass nitrogen, which I'll come back to later. And therefore, there was a lot of image that needed to be analyzed, or rather annotated. But looking at the manual aspect, that will take a lot of time. So I used this deep learning network, which is abbreviated as you only look once, which is abbreviated as YOLO. And what this does is that I was presenting it with images, which I pre-trained, and then telling it, tell me what animal you're seeing there. So for instance, in this, what it tells me about the first 3 is that 100%, this is a wild beast. But the 2 here where we have the dotted line, it's telling me that here, I think this is a wild beast, but I'm not so sure whether that's true. But as you can see, there's one beast here without a bounding bounds. And so what they tell us the level of certainty and also the species level. So at this point, I would go and do the manual annotation, just looking at this, and tell the model, actually, this is a wild beast, so classified as such, and also this is a wild beast, you've missed this, so classified as such. So I did that separately to train the model, and then I went on to analyze that data, looking at, in camera 1, was there a wild beast or a zebra recorded? Because those are migratory wildlife species in Serengeti, and they all move together. Was there an animal detected between 7 and 6 p.m.? And therefore, next, I wanted now to add in other covariates or other predictors to understand what are the drivers of this spatial distribution. So, sorry, I need to move to the next, but it's not responding. Just give it a few minutes to see. Yeah, here we are. So I wanted to model presence or absence of migratory species as a function of distance to the boundary, change in NDVI. And this change in NDVI is a metric that we use to tell us whether the vegetation is greening up or is drying. That has an influence because these animals tend to track the green resources throughout the year. And also grass nitrogen also comes into play, because it's like when I give you a queen cake vis-a-vis ugali, one is sweeter than the other, and you're likely to go for the one that is sweet. So I wanted to look at weather presence or absence at any given camera trap is as a function of all three variables. So what I found is that actually in Balageti, which is A, and Tabora, which is B, animals tend to be in areas away from the boundaries because these areas are highly transformed outside the park, are highly transformed. We have the community there, and also they have transformed these areas. But in areas where we had sort of what I'm calling a soft boundary, uniform, like in this case, you can see down here C, which is Buka, there was no any pattern. It was like either you are close to the park or you are not close to the park. Ideally, meaning that all the regions were being used in equal proportion. But here we see that these animals tended to avoid areas that are close to the boundaries. So that is one just looking at how we can use camera traps to and use it in a way to extract data and make some ecological insights. So this one I'm just presenting aspects of machine learning and one of the tools where we use to track animals. So if you look at it holistically, you realize Serengeti has about 110-kilometer boundary, which is very hard, and that's about 17% total length. And therefore, the take-home message here is you might have that effective conservation area, which is actually smaller than the geographical or geographic sites. And what do I mean? You have that area that is close to the fence or close to the boundary that has been affected because of human activities. But animals actually don't go to those areas. Yet you dedicate resources like patrol people to go and protect those ecosystems, and they are not used by wildlife. Therefore comes the question, is that value for money? Are you getting value for money? Or you need to, re-strategize and think about how you're going to use those resources elsewhere. So this strategy, you realize, just used three transects, but it would be more interesting if I could get some time and use more transects and also look at tolerance of different species, because not all species will be respond to such landscape transformations. And also aspects of seasonality. What will happen, suppose we have a long wet season, with these animals still about those areas, or they will just use them in equal proportion. And I want to point you to this paper. It's already published. You can go and read more about it. So I invite you to take some time and read about it. There's a lot of information there. So next, I want to take you to our second question. It's not going to the next slide. Just give it a few minutes. See. Yeah, there we go. And in this one, I'll now focus I'll be talking about integration of different data streams. And this one, I focused on automated and repeated diary observation of GPS-collared animals using UAVs and open source electronics. So one thing, when you look at this photo, it's a bit of structural similarity. For instance, we have this one here. These are word-based from, this is an image from satellite. And down here, which looks like a stamp, they seem to be something like a predator. And these word beasts are whirling around that, try to confuse that word beast. Again, down here we see fish, and all these salmon fish are just whirling around a shack. And both A and down here, we see a lot of structural similarity in terms of the expression of behaviors. And here the word beasts, they are lining up or forming a linear structure at crossing a river channel. And down here we have insects doing the same. And when you look at this, again, it's away from, whereby in front here we have so many word beasts, but right here at the back, they are not so much. So the pressure is at the front, but the low pressure is at the back. So looking at this all together, you can say there's a bit of coordinated movement that is taking place. And one could ask ourselves, so who is coordinating this movement, or who is copying who? Because someone must have started this movement and someone's followed, but there's an individual somewhere inside here which is just following because the nearest neighbor started moving, and therefore that exchange working. The goal is just to start moving or following these animals. But there must be a bit of consensus building, because they could have gone either direction. Maybe they could have decided, let's cross the river channel at this point, or let's actually not cross this, just go back to the opposite direction. And therefore, looking at all this, we then ask ourselves, that how are we able to collect such kind of data to understand aspects of collective behavior, collectively navigating wildlife species? We've had telemetry data that has been suitable for long-term individual studies. And that's good when you're interested in individuals that, they range alone or they don't really move as group. But what about when we're interested in short-term collective behaviors? Can we use drones? Because that's that's another thing. And then rather than using drones, is there a way to integrate those two such that you also get the telemetry data and the observation data of the individuals or animals that tend to move together? Here is a case in point. Look at this animals here. There's a group here where we have number 14, and they initiate the movement. And this other group down here where with 20, those ones are going in the opposite direction. This one, group 0, where we have 0, 2, 4, we see, okay, the nearest group is moving, it's time to move. And as you see, up here, we see some animals that are coming, or rather, following the suit. I'll play this again so that all of us can see. From your end, it will be a bit shaky, but from my end, it's very clear. So we have this group that initiates the movement, then this one with number 14, move in a different direction. At the same time, we have this group here with number 0. They start moving the first group that went towards the bottom corner. And therefore, you ask yourself, who is making these decisions and who is deciding which way to go? For instance, in this case, what we see is an individual made that decision, and that decision was copied by another. But using long-term telemetry data, you miss that information, which is very critical. And therefore, this leads me to the question, then how do we fuse these two data streams together to collect not only location data, but also the behavioral data? So one way I thought about this, or we thought about this, is just coming up with the concept of automated and repeated observation of GPS colored animals. So there are a number of companies that are manufacturing open source electronics. And when I talk of open source electronics, these are electronics that you can use and program yourself to do a specific set of tasks. So there's Arduino and also the Raspberry Pi. So we have like these two companies that are well known. So what they produce is something like this. For instance, here I have a GPS, which is the one you see, and you can power it using a coin cell. Conversely, you can, draw power from a tri-cell, which is bigger than a coin cell, and power this GPS. This one is a LoRa board, a LoRa for long-range network, and therefore this one is for communication purposes. So I used this to come up with what I'll be calling a GPS, custom-built GPS tag. Down here, we have a Bluetooth module, the chipset. And what this does is gives you that ability to program and come up with your own Bluetooth network. And this one is just similar to this. So for these two are for communication, what we call peer-to-peer LoRa communication. Down one here, this one, the last one here, it's just like a normal screen, just to show you things that you're printing out in your devices. So these three, I use those to come up with what I'm calling base station. So the final product is something that looks like this. So this is the GPS collar with the two combined, and down one here is the base station, which both have to communicate with each other. And then I went on and designed this 3D casing. They are not waterproof. I used this one for the prototypes, and and then this is now what I had at the final end, is a closed GPS collar and a base station. And you can see here, it's telling me what B to go to standby, and it's giving me the signal there. Something that, it's communicating, and it's telling me the GPS, it's activated. So what is the concept that I want to share with you here? So first, we have a drone, and we have the custom made GPS collar. And then we have the operator with the base station and a tablet. So what I did here is that this one, the collar, is programmed to turn on and turn off periodically, and because I don't want it to be on all through, but just to turn on and listen for any incoming message. But then on the other end, we have a base station that is plugged into power source, and then it starts broadcasting wake up messages, like, sending messages to any GPS caller in the vicinity that's, attached to a word piece. If then there's no caller, then what the base station does is that it doesn't get any acknowledgement message. And as the operator, after some few minutes, you just disconnect the power and move to the next location. However, suppose there's a GPS caller attached to around. What you get is that it acknowledges that message as at the base station. What you get is a caller ID saying maybe word beast 1 or word beast caller 1, something like that, that identifies the unique caller that you're connected to. Once that is okay, if I want to proceed, then I'll say proceed to high broadcast mode. And what that means is that I want now to start generating frequencies or GPS frequencies at 1 second. So every second I get a GPS frequency. Every second I get a GPS fix. With that happening, so this information, I want now to use that information. So once it switches to high frequency mode and broadcast those locations, it sends them over the LoRa network to the base station. The base station will receive the GPS fixes and forward to the tablet. And the work of tablet is again very easy, is to control the drone and to control in this manner. The drone has its own GPS location. But what I want this drone, the tablet to do is to bypass its own GPS location by spoofing that its own GPS and feed the locations received from the base station to the drone. Therefore, the drone has a ledge app that I was using, and this one implements the follow me. So what it does, the drone is strict that actually you have to follow the tablet, but actually the tablet is next to the animal that is collared. So what it does is that now you automate that process because you are getting all these fixes from the GPS. They are forwarded to the base station, to the tablet, and finally to the drone. So the drone now implements the follow me, and now you can start the recording of those individuals, the collared one and the nearest neighbors. And you do that automatically. You don't have to do anything else. So you automate that process, and you're able to record a collared individual and over the nearest neighbors. So when I was doing this work, I thought of initially the plan was to come to Serengeti in Tanzania, but again COVID happened and I was not able to fly back to Tanzania. So I thought of using a different species called ponies, and ponies, they are in Scotland. They sort of look like horses, but they are not horses. They are a bit smaller in terms of size, but very stocky. And the males, they have these like mane like, and also they are not really wild. They are semi-wild or breed, and it's being used for conservation purposes in Scotland and other areas in Europe. So like in this one, I was able to, with a bag of carrots, this one was able to come close, and I would attach my collar, which you see here, collect my data, and then remove the collar and take it back with me to my place. So in this slide, I just want to show you a short clip of the automated tracking system in action. So basically, it's just automating everything and following the collared individuals. So things to note, this individual here is the one that is collared. These guys are very lazy, so they spend most of the time sleeping. As you can see, there's a lot of grass, so they don't move a lot, and there's also no predators around here. So it's a good environment for them. So this guy is the one that is collared, and we'll see as we progress. So you can see nothing is happening standing. But then at some point, they start moving, and the drone now is adjusting to make sure that it follows the collared one. And as you can see here, now it has changed direction, and the drone has adjusted. But there's another one here, individual. The one that's now leading, that one is not collared. The second one is the one that is collared. They're basically just here to demonstrate how I went about collecting this data. So with that, I had to look at, case study. Is this system really working? The only way is just to present some data or some results. So what we see first here is the position of the collared individual in relation to everyone else, or in relation to body lengths. So this is distribution of the body lengths for all the individuals is the dotted line, which is about 9/4 body length. Body length, I mean, like in this red triangle here, that's the body length. So the collared one which is here in this box here, the red bounding box, is about 2 times the body length of that individual, meaning that mostly you will find this collared individual close to the center of the frame. And that's the most important thing, that this system, I designed this system to sort of keep the collared individual at the center of the frame, and also the nearest neighbors be able to also collect information about that. What about if you want to look at now these aspects of collective behavior? It could be more complex than what I'm presenting here in panel B, but for panel B, it's just looking at simple metrics that you can extract from this data, looking at nearest neighbor, or second nearest neighbor, or third nearest neighbor. And this comes into play when you want to look at how animals respond to different levels of threats in the ecosystem. Do they form encamped behavior, or do they, form on disordered phases, and in which areas do they have these different spatial or organizations? So in this one, it's just presenting a pretty simple metric that you can extract from this data, but it's more than this, because here I was just interested in sort of presenting the concept. And here it's just for visualization purposes. So note that I've cropped these images. It's quite big, it's a high resolution image. And this animal here, bounded by a red box, that's the one that is colored, and the blue dot here indicates the center of frame. And therefore, it gives us an impression of how this animal is close to the center of frame. And all through, when I was tracking, it was about 2 body lengths at least, which means, and therefore this sort of tells me actually this animal, the system is able to collect information of these social animals, the colored one, and also the nearest individuals. So one thing, by the way, this work is coming out very quickly, and I mean, in the near future, it's now doing undergoing some sort of typesetting. It will be published in Ecosphere, so keep an eye. So number 3, I'm also interested in, now that I'm able to track animals and track them at a group level, what about enhancing that and looking at the fine scale behavior? And here I present another approach looking at high resolution data. And remember, high resolution data comes at a cost. You need to think about transmission, storage, or processing, and analysis. I looked at how can we then develop a near real-time classification of Serengeti behavior with edge machine learning and long-range Internet of Things network. So the motivation is that we have GPS that gives us the information about, or the location of an animal, but it doesn't tell us exactly what this animal is doing. Although using machine learning techniques, we've been able to develop some metrics to understand whether these animals were moving, or they were just either encamped behavior, or moving, or just an exploratory behavior. For instance, one has been looking at the frequency of those, or the distribution of those animal locations, and in a way, you can see an animal is having a short step length, because you see that the locations are quite tightly close to each other. But that's quite general in sense that it could be doing other things, but it's only that because you don't have data to validate that, you just settle for that. For instance, this animal could be short steps length, but it could be actually it's grazing and at the same time being vigilant, or it's just moving a few steps and then stops, scan the environment, move again, stop, scan the environment, or it could be actually resting completely. And you're interested in those areas whereby these animals have that courage actually to rest, or to lie down and rest for some minutes or for some hours, because they are in a natural world. Therefore, with this information about, what about integrating 2 systems? What if I bring in something like something that is able to give me data about the 3D axis, and I thought of accelerometers. Accelerometers, they collect data in X, Y, and Z movement. But alone, you can still get data and analyze that. But you can enhance them by adding something that also gives you the tilt angle, the pitch, and roll. So once you add that gyroscope, it now moves from 3 axes, it comes to 6 axes or 9 axes, depending on how you want it to be complex. And in my case, I had it with 6 axes, which I'm calling inertial measurement unit. So what this
devices do is that they detect those motions and they detect them at a very high resolution or very high frequency. So for instance, it could range from 1 hertz to 40 hertz. What it means is every second you get an observation, or it could be every second you get 40 observations. So if you translate that into seconds, minutes, and hours, you realize you generate millions of observation within a very short duration. And what you need to do at that point is think about how are you going to transmit that huge data, especially in near real-time applications. So for instance, what about using machine learning or edge machine learning? What this means is processing data at the source and transmitting the output. So what I did here, yes, the slides are not moving. Okay, so what I did here, I was lucky to work with the Tanapa, Tanzania National Parks, and what these people have is that they have developed LoRa gateways that are strategically placed throughout the Serengeti National Park and also the surrounding conservancies. So the red dots we see here are locations of those gateways and primarily set to monitor key species like rhino. They get the feed data about rhino locations, and also they want us to know where their vehicles are, and at the same time look at also the speed of those vehicles and be able to manage the resources better, because we don't want a car that's using 100 kilometers in a park. We want to get that information and possibly penalize the person doing that. So with this system, I was able to get a chance and now also embed our system so that we can also generate or get another data using this infrastructure. So a gateway is something which looks like this. This is one that had a few issues and we were here to fix it. There's someone up there. It's only that you can't see. It was a bit foggy. It was this one here, next, very close to Ngorongoro Crater. So that's why it's very foggy. It was very cold. So in this case, I developed this LoRa collar. I'm calling it roller collar, and basically as components like this one, it's a LoRa board, and this LoRa board also a computer that for machine learning. This is the GPS. With both gyroscope and accelerometer. So this is the IMU, and the green board is one that I used to control power from the solar panel here to the LiPo battery, which is beneath. You see this group here. That's the housing for the battery. So once all this was put together, this is the final product that I had. You got the solar, the top case, and the lower case. So first, you need to collect data, and I needed to collect that data from a similar species, and that was the wildebeest. It was somewhere in a place called Kiligof. It's about 45 minutes drive from Arusha, heading Moshi. So it's a place called Kiligof. They have this facility whereby the gophers are space to come and practice, but they also have captive animals. As you can see, we have elands, we have wildebeest, we have zebras, we have imbalas, and some more. So I collared 6 individuals with this collar here, and this one was a bit different in design. This one used, rather than using the LoRa board, I used a Wi-Fi board because I needed transfer. And this was because I need to transfer lots of data within a very short distance. And Wi-Fi is good for that, unlike with LoRa, which is a low bandwidth. So to collect data, I had to tag that animal and observe what that animal is doing and record the start of that activity. And once it switches to another activity, record that. Once it switches to another activity, record that time. So I had several gadgets working together. So what you see here is the wildebeest that is collar. Right? And in my laptop here, what I was reading is this information. It's 6-axis data. So 100 meters. The observer. Also, we had a camera just to record this, and in case we need to data, with some spikes in the data, we look at what this animal was doing. Possibly it was in a very weird position, and that's why values went very high, and it was really, really important later in the analysis. So this was the training data that I had to train to look at that. So the model, I used the convolutional neuron network. And this is the model structure, quite simple, not so many layers. But the most important thing is looking at the accuracy of this classification. And overall, the model had about 84% accuracy. So different when looking at the different behaviors, grazing was pretty easy for the model to classify that or predict that at 94%. Lying was 89, standing was 79, and then walking was 82. However, you look at this, there was a bit of misclassification because of the, the way these behaviors transition from one another to, from one another to another. For instance, walking and standing, it's pretty easy for an animal to walk, stand, walk, stand, walk, stand, walk, stand. But it's not very easy for an animal to, move from walking to lying. It has to first walk, stand, and then lie down. So that was a bit of, but overall, the 79% is still acceptable. From 75, that will be a bit easy for classification to be, accurate. Again, the other thing could be because of this system, in these captive conditions, there are no predators. So these animals, although they will be able to see in their natural environment, still without predators, some of the behaviors are lost. Therefore, maybe with Serengeti, what with these things is likely to achieve better classification. So after I trained my model, I went to look at the what is known as Serengeti and colored someone is talking, and then colored the word beast, 8 of them, and then used now the LoRa color with the models. Now I started getting that data. So first, I wanted to look at how can you validate this information given that you are not able to observe these animals in the park. And the reason is because I tried to observe them and validate the data, but I followed them for like a minute and then I lost them. We had 4 people following with binoculars. Somebody said, oh, I have it standing left, going to this direction, and then all of a sudden, oh, we lost it because they congregate in so many numbers. But what this plot is telling us, distance walked between points, that's hourly interval, and these are categorized proportions of walking within that hourly interval. So here it says a lot of walking activity. It's that was recorded within that hourly interval, and that is what I see, because that proportion is very high. And what I see is that also the distance was also very high. If you look at this other plot here, I'm looking at the probabilities of these 4 activities. Either you're grazing, you're lying, you're standing, or you're walking. And for instance, if we pick the blue one, lying, we see as the distance increases, chances that these animals lying is also next to 0. And this means that the model or the algorithm actually managed to classify these behaviors the way I expected. So now looking at the other aspect of behavior, I need to move to the next, just a minute. Yeah, looking at now the behavioral fluctuation throughout the day, what we see is that the model actually is able to capture those fluctuations in behavior. For instance, our big grazing, and we see during the night, very minimal grazing takes place. But from around 6 or dawn, starts to peak and peaks up to around 9, 10, and around 11, they usually stop grazing that much. They'll be just grazing a bit, then lying down or start moving to the nearest water source. And that happens exactly like that. But then as from 3 onwards, grazing peaks again, and then at night goes down to, about 20% or 10% grazing activity. So again, if you look at lying, at night, it's very much lying because again, you want to minimize as an animal, you want to minimize movement to make sure that you minimize encounters with predators. But also during the day, because there is a lot of grazing that is going on, we see that from the model, we are able to capture the activity as lying very low. And also all these other activities, but walking again at night is very minimal, but during the day, there's a lot of walking going on. And this one is just telling me, yeah, the model is working, and the system, the caller is able to capture this data, analyze, and send this data to the end user. So conclusions and future plans of so this work is, I have all the prototypes working and I've tested them now, but there are lessons that I've learned, and these are things that I want to work on before I can do another deployment. So firstly is to deploy more collars, especially the observation one, the drone one. But that one, I'll need to enhance the design so that it's able to remain in the field for long. That's incorporating a solar panel and also a reliable rechargeable battery. And also for the real time, the model worked. Therefore, now it's just to upscale that. Now, change the design a bit. For instance, things that I learned, the drop-off mechanism that we designed did not really work as we expected. There's one individual that dropped the collar just in minutes after it was up, but this was because it was shaking very vigorously, and that this is now the next phase of this work of developing these tools. And yeah, what is happening? And next is just a minute. Okay, yeah. So this work has involved so many people, and I'm particularly grateful to these two guys here, Colin, Tony, and Brian Hopcraft, and other guys in Tanzania, and also at the University of Glasgow, and other institutions that were also supported this work, and also several research grants from other organizations as well. So this is what I had prepared for you today. Although we had issues with the internet, I think you got most of it. And yeah, that's the end.
Thank you. Thank you very much, Dr. Cyrus, for the insightful presentation. In fact, it has been a real tour across the Serengeti, across the Mara, tracking these wild beasts. So, yeah, we'll just quickly go through the questions that have come through our chat box, and I will start with one from Clinton Shoso. He's asking, what AI software did you use for annotation? And the same Clinton is asking, how much did it cost to construct the GPS gadget? And the last one from him, how does the system detect whether an animal is walking or standing? So I think we'll handle that first before we go to the next participant's question.
Yeah, actually, that's a very good question. Actually, I like it. About the annotation, there's a paper that was published in Methods in Ecology and Evolution. It's about annotation interface for data-driven ecology. It's abbreviated AIDE, AIDE. And what these guys did is they came up with an interface whereby you can upload your photos on Azure or another cloud storage, and you'll be able to pick them from that storage and analyze using these AID. So AID borrows a lot from YOLO, which is a neural network model developed for computer vision. So this is the one that I used to annotate. The only downside is that you have to buy a license for you to be able to use it, but it does very good job. About the cost, for instance, the ones that I showed, you remember that small, the GPS and the LoRa board. Both of those are less than 30 pounds each. And then other auxiliaries will be about £1 each, like the pins to connect the two pieces together. Basically, an entire collar, I would give it 350 pounds. If you compare that to the commercial ones, which is going at around 2,000 euros. Therefore, you see there's a lot of difference in terms of price. Sorry, I missed the last question. Repeat that.
Okay, the last question was, how does the system detect whether an animal is walking or standing?
Okay. Right, yeah. That's also a good question. And what I did is first I had to collect a training data because the system has to see some data, or what we call supervised machine learning. So what you see like in this video, there's this what is that playing on my
Yes, it's playing.
Yes, so I'm collecting this information. Now this animal is grazing. So just click on the start grazing and just wait until it changes. And now I'm getting this data at my laptop. So this is the data that I used now. I cleaned and analyzed. Then I trained a model that it's able to tell whether this animal is grazing based on the data that it has seen before. And now with all that information ready, I created a model, and that model is one that I uploaded in the collar that I showed a bit earlier here, this one here. So this scholar as a like a mini computer, and that mini computer is able to run that model and say, okay, I'm getting this information. So what does it look like? This is the model. So the model says, okay, now this, I think this looks like grazing, or this is walking, because it has seen the data before. So basically that's how the algorithm is able to tell the animal is grazing or walking or doing another activity. Yeah.
Thank you for the responses to Clinton's questions. There's another question from Teresia Mukai. She's asking, can this automated GPS be used to observe and monitor the movement of turtles? If not, what can I use instead? Its costs, and also how do I analyze and interpret the data collected?
Yeah, that's also a very good question. And yep, for turtles, I don't think do they dwell in deep waters or in shallow waters. That's the first thing you need to look into and figure out, how do I get a housing that is waterproof, actually, which is now my next move after after having developed all this. So first you need to be consider that, do they dwell in deep waters, or am I able to get that signal, or the signal will be interfered with? And if not, then it means it's impossible to use them there, because you need to be able to generate these fixes and to transmit them to your base station, and then from base station to the drone, and therefore do the automated tracking. But for terrestrial mammals, then it's possible, because once the animal is outside range, what the drone does is just, it stops at the last known GPS location, and you as the operator, you just take over the control and draw the drone back to your launching site or wherever you want it to land. So that's a bit tricky. If you can't get the fixes, then you can't use it. You have to think of other ways of collecting that data, and mainly to be different GPS that will be able to record that information and capture that and extract that information. Yeah.
Okay. Thank you. Thank you very much for that. There are two questions from Lydia Rose. One, she's asking, thanks, Cyrus. This is a very impressive work. Where do you store and process the data? Do you have any computing facilities here in Kenya or Tanzania? And the second question goes, also, I was very impressed by the network of LoRaWAN gateways in Serengeti. Any chance that it is extended in Masai Mara? Those are the two questions. Yep.
Yeah, let me try them. Yeah, thank you again, Lydia, for those two questions. Very impressive. I think there's something that I worked very fast, and I'm just going back to it. Tell me whether you can see the two electronics or the gadgets. So to answer the first question, where do you store the data? The way I had this system is because, remember, we are talking about near real-time classification of animal behavior. So this LoRa ball has a small storage facility. But what it's doing is that it collects this data, analyzes it, it will turn and collect data, analyze for the next 30 minutes. And then if it's within the network average, that's the LoRa network, it will transmit that data to the network, to the LoRa gateways. And now the gateways transmit that information to the servers. So you need to have a way to collect it, get that data or download it from a server. So what I had is that there are these LoRa gateways connected to a server. And then if these callers turn and are connected to the gateway, they are able to transmit that data immediately. And if not, then they will just store it on board and then transmit it when next in the range. So that was the transmission process. Because again, you find Serengeti is very big. Most of these LoRa gateways, they get struck by lightning. They don't function as they should. You have to keep on repairing them. So that's basically how I approach this, because you don't want to lose this caller at the same time lose data. So you have a system that uploads it as it's being collected, analyzed. You get the final output. And maybe something worth mentioning is this thing here. So I had this data encoded as a binary digit. For example, 00 will be grazing, 01 will be lying, 10 will be standing, rather than having it as grazing, lying, standing. That's because this means that I'll have a lot of data at the end of the day, and I need to figure out way to shrink that data and make it more meaningful, and also be able to transmit it to very long distances. So if you have a lot of big data, the transmission is over short distances. If it's very minimal, then it's over long distances. So those are the compromises with the LoRa network. About chance of this happening in Imara, for now, I really don't see any plans, or haven't had any of these plans. But possibly, I know there are some meetings that will be happening very soon, and I think next month, or next month, possibly they will consider this, because we want to share this technology with them and see whether it's something that really excites them. And I think it will be very beneficial for both ecosystem, both Serengeti and Masai Mara. Thank you for that. Do we have this other question?
Oh, okay, thank you. I think in a nutshell, Lydia's put it this way: where are the servers?
Yeah. Oh, where are the servers? For this one, I used Microsoft servers. So you have to buy a space and then figure out how you can utilize that, or rather a decoder that will get these numbers in zeros, in ones, and then analyze this information. Because this is not what you get. You get very many numbers, but you need something to decode that, and therefore you're able to log in and download that information. Possibly, if she's interested, we can also set chat about that. Yeah.
Yeah,
So Microsoft is an option. Azure is also an option. They have those facilities.
thank you very much. There is a question from Dr. Simon Musila.
Yes.
Yeah, I think he's the patron of our mammal committee, and he has a very interesting question that I was also asking myself. How did you choose the first wild beast to collar?
That one is yeah.
And
That's a good
two,
one.
yeah, he has two questions. And
Yeah.
two, in terms of acquiring permits for your research work in Tanzania, what was your experience compared to Kenya if you were doing the same study in Kenya?
Yeah, experience the permits.
Yeah.
I think yes. I don't know. He is inspired by the experience there, but that's a very good question. One is, how do you choose the word beast to follow?
Yeah.
Sometimes it can be a bit challenging, because if you look at this one, looks a bit healthy, and if you look at this one, it is very skinny. Where the one that I used for training data, because the conditions were not right. This point, when I went for the reconnaissance survey, it was just bare ground. It's like it rained here, but luckily after 2 weeks it rained. They started raising. Basically, when you want to follow, you need to health one, not as a burden, but an adult, and not their own one, because you don't want one that will be taken out by predators. So basically that's all. But it could also depends on the question that you're interested in. For instance, in the case whereby you want to look at the transfer of information and personality, you could look at the males, old males, young males, old females, young females, and such consideration. So basically, it depends on the questions that you want to answer. But for my case, I just went for the mature ones and call up. The second one about permits. Yep, that's a good question. And I would say it was a bit difficult to get all these permits together because, for instance, the drone work. If drone work is not so many people are really appreciative of or rather we don't have the legal framework changes from one country to another. So in this case, you see here TPDF, Tanzania People's Defense Force. I had to be vetted by Tanzanian Defense Force, and this took some time because they don't know exactly. Although I've said that I'm going to do research, they really don't know whether it's research or I'm going to do other things. So first it was this one, then it was Tanzania Wildlife Research, then it was COSTECH. But the bad experience is that some NGCs took longer than I expected. And then, for instance, Tawiri would clear me, and then by the time I'm being cleared by COSTECH or TPDF, the first permit has expired. So it becomes like a cycle. But towards the very end, I managed to get everything together. So I think if I would go back there to apply for the permits, I think it would be a bit more easier now that they are used to, drones in Serengeti and other ecosystems. Possibly it would be a similar case in Kenya. I need to contact the Kenya Civil Aviation Authority, show that I've been trained as a drone pilot, which I really did, and also show other aspects like the manual. There's a manual that you have to prepare, especially if you're doing the drone work. to show that you understand the airspace and how to use it peacefully with others. So it's a bit challenging, but yeah, you eventually get it at the end of the day.
Thank you. Thank you for that. There's another question from Margaret Vaz. Hi, Margaret. She's asking, the data seems to indicate that our wildlife is already under threat from human behavior. What is being done with your data to minimize the effects?
Yeah, that's a very good question, and I like it. One thing what we're doing here is we're generating this information, sharing it with the managers. For instance, like this month, I'm talking about there'll be a meeting between conservationists around Mara and Serengeti, and they'll be sharing more of this information. So what we do is tell them this is the information we have. For instance, the last meeting, that the one aspect that came out was that wild are spending 29 days less in Kenya than they used to. So, and they were like, then what should we do? We open up the areas that have been fenced, because those are areas that these animals used to go, and that's why they were spending more days here in Kenya. And the community took that positively and brought down all the fences. So basically, it's not a straightforward thing. You need to convince people very, very much, because people have different interests. There are those interested in livestock, those interested in wildlife, and also make tourism benefits. Make sure they reach those guys who have given up their land for the animals to use. So, for instance, in Serengeti, what they are doing, they are trying to communicate. After this information, they are talking with the communities to tell them, is there another way we can support you to stop some of these activities? Because if we tell you do not encroach, or we tell you do not do this, can we buy off some of this land and we relocate you some willingly, so that we create a boundary or a buffer zone around the conservation areas? But remember, these will require a lot of conversations, a lot of politics will come into play, and a lot of resources as well. So it's not a straightforward thing, but yeah, we need to be aware of that. Maybe the most one is just consider adaptive management strategies, because the problem is already there, but now you need now to adapt to that and mitigate further deterioration of the ecosystem.
Thank you. There is one from Ropi Mangat, more or less the same. Are governments in both countries using this data to protect Mara Serengeti?
Yes, like, yeah, that's a good question. Like now, in that meeting, we have both researchers in Kenya and managers in Kenyan side, and also researchers and managers in Tanzania. And they all meet in a conference for about 3-4 days and talk about the research output from both systems and see how are we managing this ecosystem. So and that's why I mentioned, like, the next meeting, there will be a conversation about LoRa network in Mara, so that we can also get the same information as we're getting in Serengeti. Because these animals, they don't know about Kenya or Tanzania. They just know this is where we have to go and graze. But one in Tanzania, in Kenya, you should be able to get that information and also map these areas where these animals, they just walk, or areas that they will just go and lie down. So a bit of information sharing is what we've been advocating for.
Thank you. There is one last question from the chat box from Leo, our chairperson, normal committee. He arrived relatively late, so there's a question that you've already answered. His comment is amazing talk, Cyrus. How did you decide which wildebeest to call her? Can you identify the exact individual who is initiating the group behavior? If yes, what's unique about those individuals? Lastly, what are some of the constraints of these methods, or can they be easily applied to other species?
Yeah, again, thanks a lot, Leo, for the question. They are really nice questions. I like them. First one is, how do you choose the individual to call her? And earlier on, I mentioned that it's based on the research questions that you want to answer. For instance, in this case, I just want a mature wildebeest. And if I want something long-term and I want to look at the social, or rather the collective navigation, I would go for the females, because they don't leave the groups. They hang around throughout their their life. Unlike the males, they will split at some point, or the groups splits. But also females make sense because they have an additional activity to take care of the young one and also take care of themselves. So the cost is very much as compared to a male. So in this case, I'll just go and say, okay, I want a female and call out the female ones, especially the lactating one, because I want to look at the cost of, lactation vis-a-vis when not lactating. But in this case, for my work, I just wanted to look at one and then call out that one and just look at the behavior. So I went for the mature ones for grazing, walking, and all those sort of behaviors. He said, is it possible to identify the one that initiates movement or something? Yes, with the system now, you can look at those small groups and look at which one is in front, because there must be some sort of consensus building. When they start moving, they all move in different directions, but at some point they just converge and agree. So we say a consensus has been arrived, and now they are moving in the same direction. And this is because possibly the one that is initiating the movement is more experienced than the ones that are copying what the leader, sort of leader follower aspects. So for now, I can just leave it at that point because I have something going on that I want to look at now, those aspects of leadership, personality, and information sharing, and all those aspects of collective behavior. So possibly, if I'll get a chance, I'll be able now to answer that questions more concrete. I think there was a third one. I forgot that.
Yeah.
From Leo.
Yeah. He was asking, what are some of the constraints of these methods, or can they be easily applied to other species?
Yes. Developing of the methods is quite involving because you need to write those programs yourself. Program that caller which says, okay, it's this time, I need to wake up and listen for this message. If there's no message after this number of minutes, I go to low power mode or sleep mode and wait until a certain duration has passed. So you need to be able to do that. And one way to circumvent that is just embrace collaboration with engineers or mathematicians or people who can be able to do that. And then you learn in the process. But we also have guides like from MicroPy. They have guides for people to be able to play around with those gadgets. Like, you want to change that GPS fix to collect a GPS coordinate every second or every hour. So there's all that information. So that is one of the constraints. If they don't have the technical know-how, then you'll be a bit challenged. But if you outsource that, then you're able to work with others. Maybe setting up the LoRa system is a bit expensive, but collaboration again comes handy because you can do lots of activities supported by that LoRa system. So basically, it's about that. But in terms of cost, in terms of the questions that you're likely to answer, it's way, way better. Massive information can be generated compared to the off-shelf GPS collars that we have in the market.
Thank you. There is one last question from Suhail Mohammed. Does the drone have any effect or no effect on the animal's behavior in the field in your observation in terms of visual and the noise?
Yeah, thank you again, Mohammed. That's a very good question. Yes, the drone affects the behavior, but you don't want to affect or rather influence their behaviors. So what I used to do is first do the trials, identify a launching site, launch my drone, and usually fly away at an angle until I reach the ceiling height, which is around 400 feet, 120 meters above that ground. And then you can try different models of drones. You can try small ones, you can try big ones. In my case, I was using Mavic 3, which is relatively small and a bit silent compared to Phantom DJ that I had sometimes back. So in this case, you have to fly and then start going down above the animals slowly and observe their reaction. If then they react to that, buzzing noise, then you know it's affecting them. If they are not, then you know it's not affecting them. But one thing I learned is also that, which was really, really bad experience. You launch the drone and then birds of prey, starts flying in, thinking that there's something that is interesting there. And some can be very nuisance. They can take the drone down very quickly. So you need also think of insurance. But basically, you just go high as possible, then go down slowly and observe the animals until you get the optimal height. For my case, it was 80 meters above the ponies, the ones that in Scotland, but in Serengeti, it was 120, and they did not react to the drone. And it was very, very, very silent at that altitude.
Okay, thank you. Thank you very much, Dr. Cyrus, for going through all the questions that came through the chat box. We have comfortably handled all of them. So maybe I will give our audience maybe one or two an opportunity to ask a question. If you can just raise up your hand, we give you an opportunity. You have our one-on-one interaction with our speaker before we bring the session to a close. So the floor is open to any of our participants. If you want to, you can raise up your hand. We unmute, and then you ask your question, or even give a comment, give a compliment. Hi, Margaret. You want to ask something?
Hi. I would just like to thank you for all your hard work. How many years have you been putting into this? And also, it must be very hard to be able to present this information. Where on one hand, we're talking about tourism, and on the other hand, we're talking about the animals. And I think that that is a very, very difficult conversation to have with your partners. But I would like to thank you for your research and keep going. Thank you.
Thank you. Thank you very much, Margaret. Are you asking your question from Canada? Or you're in Kenya currently?
I'm in Kenya right now.
Okay, good, good. Thank you very much for your comment, your compliment. We really appreciate it. Thank you. Any other person before we end the session? Yes, Dr. Musila. We can't hear you. Dr. Musila, I think your mic has a problem. We can't hear you.
Okay, can you hear me now?
Yes, yes, we can hear you.
Okay, thank you very much. Okay, how are you, Cyrus?
Yeah, I'm good. I'm good. Nice to hear from you, Simon.
Nice to meet you after a very long time. Yeah, I'm also very happy for the work you presented. It's very good, and this looks like where the world is going actually. The use of technology, the use of machine learning, and I think it's very interesting, and it is something we would wish to learn more, because the kind of information, real-time data that the technology has potential to collect is what we are missing actually, and that can be used to make the kind of decision that can save our species. What I can actually say is that we are very grateful as PAMO committee that you found time to prepare and also come to present. And looking at the participants, the number was 40 something when we started, and it has remained like that throughout, which means this is something everybody was interested in.
Yeah,
So
we actually had
thank you.
I think it's really the highest.
Okay. I saw 45. Yeah, this is good. This is good. So probably you can find how you can spread the information, the knowledge about that, because I think not many people really know the kind of thing that you have done for your study. So if you can continue teaching people, I mean, they can really know what to do. I'm sure the challenge in Kenya would be permits, the process of getting them and all that. But I think that one will be solved as we go on. But it's something good that can happen. And again, congratulations for finishing your PhD. You started a long time, but I'm happy that you finished. Congratulations. Thank you so much, Richard.
Thank you very much, Dr. Musila. Dr. Musila is a patron of our Mammal Committee, and yeah, always good to have him on board. Thank you very much. Ladies and gentlemen, maybe before we bring the session to an end, Leo is here. Leo is the chairperson of our Mammal Committee, and this talk has been organized courtesy of our Mammal Committee. And I think, Leo, I will give you this opportunity, maybe just to say hi to the audience. Yeah, tell us about Mammal Committee, how the participants here can join the Mammal Committee. You work together the journey of conserving our mammals. Leo, over to you, if you can hear me.
Yeah, thanks. Thanks so much, Richard. Thanks so much, Cyrus, for agreeing to give this presentation. We really thank you for that. Basically, about the Mammal Committee, all we do is talk about mammals, try to study mammals, and to help upcoming mammalogists, or rather, generally all ecologists who are interested in one aspect of mammals or the other. So we really invite you all, if you are interested in mammals, let's chat, let's talk. To become a member of the Mammal Committee, first you have to become a member of Nature Kenya. Richard will give us the details. I don't know if the amounts have been revised, or maybe he will tell us if the amounts have been revised, like the charges. But yeah, you need to become a member of Nature Kenya, then you can freely join any of the committees under Nature Kenya, and we highly recommend that you join a Mammal Committee. Yeah, and for Cyrus, thanks so much again for that talk. Lots of information, lots of technology stuff. I hope maybe maybe we can pay a visit to Serengeti and learn about how everything goes on. Yeah, thank you so much, everyone, for showing up. Asante.
Thank you very much, Leo. As I also take the participant through, the subscription fee to our Nature Kenya membership. Maybe Dr. Cyrus, I'm sure there are some of the participants maybe who would like to get in touch with you even outside this presentation for more questions. So if you could also maybe share your contacts in the chat box so that they can pick it up from there. That whoever also wants to reach out to you, they can. Joining our membership is a very easy process. We welcome anyone across the board to join our membership. We work together the conservation journey. We have different membership categories, and the subscription fee has not been revised, like higher or even lower. For student category, it is still 1,200 shillings. This is annual subscription. For individual members, it is 2,000 Kenya shillings. And for family membership, it is 2,800 shillings. So I will also share an email that you can reach us on for more information on how you can join, and also how you can pay for your subscription fee, because you don't necessarily need to be here in the office physically, but you can pay your subscription through M-Pesa, and we will process everything for you. We are embracing technology, and actually you will get the soft copy of your membership card through your email, and that entitles you to all the benefits, including joining any of our committee. And as Leo has really insisted, the first priority is welcoming you to our Mammal Committee. So ladies and gentlemen, thank you very much for creating time to be with us this particular afternoon. It has been a very inspiring moment. And as I see, also the comments are still coming in from the chat box. Sese is saying that was awesome talk, Daktari, keep it up. Yeah, see, Dr. Cyrus, I've already shared his contact in there. Alois Wambua, great presentation. Congratulations, Cyrus. Joanne Nesbitt, that was wonderful. Thank you. Very inspiring. Keep up the good work. To our today's presenter, thank you very much for creating time. We initially had the technical hitches, but because we were actually embracing technology here, we maneuvered successfully. Thank you very much for that. And we look forward to yet another presentation from you. So ladies and gentlemen, do have a lovely evening ahead and God bless you. Thank you very much. We can leave at our own pleasure.
Bye-bye.